Welcome back. This is the third video in a series that make up the self-paced Arduino Motion Workshop. I'm Lauren, your workshop guide. If you missed the last or any of previous videos, I recommend navigating back to the video list and getting started there. Previously, we did an exercise hooking up a DC motor to an Arduino using a transistor and experimented with pulse width modulation to control the speed of that motor. In this video, we will work with new hardware and code that allows the Arduino to control when and how far a servo motor runs. Remember how in the last video I asked if you could make a motor spin the opposite direction? You weren't able to do it using code, and I sort of left you hanging. So let's discuss how our transistor that we used in the last video can be implemented to make a motor turn the other direction. Look at this diagram. Using 4 separate switches operating synchronously, you can redirect the flow of energy in a circuit, which will switch the direction of operation for the DC motor without risking any of the hardware. Each transistor can be paired, and each pair can be controlled using a single digital pin. So, 4 transistors controlled by 2 pins on the Arduino can now move your Wally forward and backward, without having to stop and unplug him in order to switch his direction. Now that we can control the bottom half of our Wally, what about the top half? We've been working with DC motors which vary speed and direction, but what about motors that can vary angular position? That is the servo. It can be positioned using a specific duty cycle, which is why we've already been introduced to pulse width modulation. The servo uses a DC motor in combination with an H-bridge controller board and a potentiometer. The potentiometer is used to determine what angle the servo is currently at, and the DC motor physically controls the rotation. So how does the Arduino communicate with the servo? The servo has 3 wires, one for power, one for ground, and a third for data. We need to hook power and ground up to the Arduino where we did with the DC motor, to the power headers. Then, the data line simply needs to connect to a controlling pin. It must be PWM enabled, but I recommend using pins 9 or 10. Pretty simple, right? Now let's talk about the code needed to control the servo. It isn't quite as simple as analog write, so we'll walk through it line by line. I recommend you start with a blank slate, either by selecting File New or deleting all your previous code. Before either the loop or setup, we have a few definitions we need to start with. The very first line, include servo.h, is what we call a library. It contains definitions and functions that help you reduce the tedious code lines you'd have to write and combines them into easier to implement structures. Using the hashtag, #, octothorpe, whatever floats your boat, include, simply tells the software, when you call a function that it doesn't recognize, go look it up in the library servo.h to know what to do with it. The next line, servo my servo, where servo is in orange, defines a term my servo as the word to represent the servo we'll be using. You can call it my servo, left arm, right eye, whatever you need to be descriptive of your project, but it will call out precisely the device that is connected to wherever you define my servo to be. This setup differs slightly from our previous method as well. Instead of using a pin mode to define where the servo is hooked up, the library has a special attach function. So whatever you called your servo, in my case, myservo.attach9, will say that the digital pulse width modulated pin number 9 is plugged into the data line on my servo. Next, let's control the servo. Under the void loop function, we can send commands of the servo to move. I'm going to command that the servo on pin 9, known as my servo, should be written to an angle in degrees, and then delay. Finally, written to a second angle and delay again. The servos we have in our Arduino kits are called 180-degree servos, meaning they should rotate 180 degrees. Unfortunately, they aren't the most high-quality servos you can buy. So, they really only operate between about 15 and 165 degrees. Lastly, why would I want a 2-second delay? Keep in mind, this is physical hardware, and physical hardware needs time to move. If you don't give it enough time, it isn't going to move any faster, it just won't get to the value you requested. So, the delay is included to give the hardware enough time to catch up to the speed of the software. Follow along as I demonstrate this code using a servo. Here I have a 9-gram micro servo. It has a red, white, and black wire. Red is for power, black is for ground, and white is for data. Let's get them all plugged in and see how this code operates on my servo. Now that we know how to control a servo, let's combine our knowledge of the material from Intro to Arduino and the material from Arduino Motion by controlling a servo using a potentiometer. The potentiometer will provide voltage values to the Arduino using analog read, and the Arduino will convert those values to degrees to be commanded to the servo. But first, what is the potentiometer and how does it work? Well, most simply, a potentiometer is a passive resistive element. It has 3 pins, A, B, and C. There is a set amount of resistance between pins A and C. As an example, our potentiometer is a 10,000 ohm potentiometer, or between the first and third pins is a resistor of the constant value 10,000 ohms. The cool trick is the center pin. Depending on where the knob is turned on the top, the resistance between A and B and C change with respect to one another, always summing to that 10,000 ohms. As an example, imagine the knob is exactly in the middle. The resistance between A and B and the resistance between B and C will be equal at 5,000 ohms each. If you recall from the photocell exercise, we can use this potentiometer as a voltage divider by applying a 5-volt signal to pin A and grounding pin C. Then, the voltage we read from pin B will be anywhere from 0 to 5 volts, depending on the rotational location of the knob. To make this computation from voltage to degrees easier, let's utilize a new function. This function is called map, and it translates numbers that you give it to new numbers. For our purpose, the number we'll be giving it will be a value corresponding to voltage and can be anywhere between 0 and 1023. Those values should be mapped to degrees that we want the servo to rotate. In our case, roughly 180 degrees. In the header, we have all the same definitions as before, but under Setup, we've now included a pin mode definition for A5, which will be the area that we can read in our potentiometer values from. We're going to store those values as pot val, and then map them to angles using the map function. Finally, we're going to send that new value, stored as angle, to servo. Give it a try using your own hardware, or simulate the design in Tinkercad. Use whatever naming convention makes sense to you, and have some fun playing around with the circuit. I'm going to move through this a bit quicker because you've seen quite a few of these assemblies. I seat the potentiometer so as to have access to all 3 pins and bring 5 volts and ground to the breadboard power rails. This is where I realize that I'm working upside down and turn everything right side up. Now, find a jumper to connect the analog input on the Arduino to the middle pin on the potentiometer. The outside pins then should be wired to power and ground. Now, your potentiometer voltage divider circuit should be all set up, so reintroduce your servo. I reattach my servo to digital pin 9. Remember, 9 and 10 are best for servo control. Then, make sure power and ground are supplied from the breadboard rails to your servo. From here, upload your potentiometer control code, and you should be all set and ready to test. Looking at it in action when rotating the knob on the potentiometer, the servo should follow suit. If it doesn't, double-check that your circuit is connected where you expect and that you remembered to include all of the new code instructions. This is the final exercise of the workshop. Give yourself a massive high five and treat yourself to a mental break. Good job. Thank you for joining me to complete this self-paced Arduino Educational Series workshop. Keep an eye out for our Level 3 workshop, Arduino Communication. As always, if you have any questions, comments, concerns, or anxieties, don't hesitate to reach out, and I hope this workshop helped you experience engineering.